make the exam so that you are encouraged to use the MATLAB coding to answer these questions. Any other concerns? I have gotten one response so far. Anyone else? Anyone else wants to? Just feel free to express. No, not a problem. Because see, this is the first time we are doing this, and especially such courses where you are tested based on your certain skill, which is like actually here it's MATLAB. So I just want to know, okay, and where there's some improvement you can suggest. All suggestions are always welcome. Okay, please let me know. If you don't have anything to say now, you can always email me about whatever you have to say. Okay. All right, let's proceed then. So I was talking about, we were talking about shooting method, right? So essentially, we were looking at the boundary value problems. In this context, we had already seen one technique which was based on approximating the derivative. Okay, and we got a matrix equation. If you recall, the tridiagonal matrix equation that you need to solve, and that will give you the value of the unknowns, the dependent unknown at different values of independent variables. Okay, so if it was y versus x, you will get y as function of different x. You first discretize x, of course. Okay, and then when you discretize, you have discrete values of x's, and your goal is to find y's at those x's that would satisfy the particular given differential equation with the boundary conditions provided. Okay, and the way to do was, so we had discussed a very simple case of the boundary conditions are such that y is given at two ends. Okay, so that was basically the Dirichlet boundary condition. It could have different kinds of boundary condition. One could have the derivative specified instead of the value itself. That is Neumann boundary condition. And you can also have more complicated looking boundary conditions, which would express the conditions are expressed in terms of the value as well as the derivative. And we'll see an example of that today. Okay. And so that was the method we discussed. Okay. And you get the answer of y versus x at all x's simultaneously when you solve that matrix equation. Now in shooting method, it's actually what we try to do is we basically try to capitalize or kind of exploit our highly accurate methods to solve initial value problems. Okay, it basically aims at exploiting highly accurate. It could be Rangan-Katta fourth order or higher order methods. Okay, highly accurate methods to solve first order. Okay, so it's like Rangan-Katta fourth order or higher order methods. Okay, so but remember the problem that we are dealing with is a second order equation. So now I'm going to, I already gave you the general form. I'm going to apply it to so I'm going to look at the shooting method. I had already told you in the last class the basic idea. Okay, and I'm going to apply it to so for example, we had seen in context with for example, you can recall the diffusion reaction in the spherical catalyst pellets. Okay, so here you had the steady state condition. Of course, we're looking at steady state, and this, if you can check back your notes, it gave you second order diffusion equation, second order differential equation. Okay, that so the catalyst is diffusing as well as reacting. Sorry, the solute is diffusing as well as reacting inside the catalyst particle, and its concentration follows a second order ODE. If you do the mass balance equation. Okay, you must have done that in quite a few sufficient number of times in previous courses, especially chemical engineers. Petroleum engineers, I have already discussed that. Please take a look. Okay, so that was second order differential equation, and here you had the boundary conditions were Ca equal to 0, some Ca at surface. Well, so here is an example of having a, so x equal to capital R, and del Ca by del R equal to 0 at x equal to 0. So this is, you see, this is an example where I do not have the value itself specified at the boundaries. Okay, so you have values as well as derivatives specified. Okay, so this is an example of kind of mixed boundary condition. Well, not the, this is basically Neumann at x equal to 0 and Dirichlet at x equal to R. Okay, and also it's a diffusion reaction. So I'm going to complicate a little bit to this. I'm going to look at an example which is a little bit more complicated, which has now flow and diffusion and reaction. Okay. So now I'm going to introduce flow. Remember, in spherical catalyst problem, the solute was diffusing in, but there was no convection. Okay. It was not convected in. There was no flow that took the solute from outside to inside. It just diffused in due to concentration gradient, right? But now we are going to look at example where you have flow also important. Okay, and now, but in a sense, well, I am going to introduce flow, but at the simplest level. So I'm going to consider, the example that I'm going to consider is basically plug flow reactor with this axial dispersion. Sometimes also called tubular reactor. So the idea is very simple. You have a pipe kind of setting, or it can be a tube with maybe a variable cross section. Okay, but it's something that you can you have something which is varying along one direction. Okay? So I mean, its shape is basically varied along one direction. It's like a very standard thing in continuous processes in chemical engineering. Okay? So it's a very standard kind of reactor, and schematically you can identify zones, which is a reactor zone. Okay, so there's a reactor zone where the reaction happens, and here I have no reaction here. Okay, let's call this, let's say that the position where reaction starts to occur is given as equal to 0, and where it ends. Okay, so this is a reactor length. L is a reactor length. Okay. And you have, it's a continuous process. There's an inlet feed, enters the reactor zone, okay, and reacts here and then leaves here. So, okay, so now we are going to consider, although we are going to consider flow, but we are going to again think of a very simplistic case, very, but actually quite relevant, which is plug flow. Okay, so plug flow would correspond to the condition where my velocity profile is nearly constant across the. If you look at the velocity profile, it would look like this. Okay. So plug flow means velocity profile is constant across the cross section. Okay. So basically, it's telling me that Vz, which is Vz over here, is constant, is independent of, let's say it's a circular cross section tube, okay, the pipe kind of thing. So it's independent of R, the radius constant. Okay. So, and also it's a constant along the length as well. So Vz is essentially constant. So Vz is also constant along the length Z. That would appear to happen when there is an incompressible flow. Okay? It's constant along Z. Can anyone tell me when does this plug flow condition applicable? When do you get this plug flow happening? In what cases you expect the velocity profile to have this kind of constant profile? Yeah, turbulent flow. Yeah, that's correct. So, well, it's actually with a high Reynolds number flow, okay, and turbulent flow, and reality it is not correct. Actually, there's a very small boundary layer that must occur because of the no slip boundary condition. Okay? So this will not happen. There is always a boundary layer, but for our problem, the boundary layer effects can be ignored because we are looking at the concentration dependence, which is mostly in the zone which is beyond the boundary layer. Okay? So we will not be worried about how concentration varies in the boundary layer. There are quite a few things which do become important and which is important when you want to calculate some quantities. The boundary layers do become important. For example, you have to calculate stresses acting on the surface, then boundary layers become important. You want to look at the heat transfer, etc. The boundary layer becomes important. But in our problem, boundary layers are unimportant, so we ignore that part, and for largely we'll assume that the flow velocity is constant. Okay, so that's a plug flow. Okay. All right. Now, so let me just state the physicality or the kind of conditions that we have to maintain here. All right. So now here, so this plug flow actually also means something else. It also means that velocity is constant. Why is velocity constant along the radial direction? Due to turbulence. Okay, so velocity is constant along z. This is due to turbulence. So if you recall, we had probably discussed it in some fluid mechanics course. I had probably discussed about some basics of that. There are eddies which are formed, and actually these eddies lead to mixing. Okay, so turbulence is arising. So eddies formation is the like beginning or onset of turbulence. Okay, so when you have turbulence, you have eddies which are actually small whirlpools of the fluid. Okay, and then that leads to a mixing of material. Okay, so it's telling me that in this direction, concentrate the species due to turbulence will be perfectly mixed. Okay, so along the radial direction, there will be perfect radial mixing. Okay, okay. Meaning the concentration also be uniform across the uh, radius. Okay, across the cross section. That would mean that concentration or the solute or the reactant that you're looking at, which is let's say Ca. So Ca enters with the feed here. A enters with the feed here with certain concentration Ca 0. Okay, and velocity is given to be Vz, which is constant. And inside Ca is going to change from here to here. That's what we want to find out. Okay. So inside the reactor, in this direction, that is in the radial direction, Ca is completely mixed. Okay, so that is one thing we will assume, right? There is no radial dispersion. Okay, so Ca is constant cross section, and therefore Ca is a function of Z only. Okay, now we'll assume some kind of first, just for the sake of demonstration, we'll assume first order kinetics. Okay, and there is an axial dispersion. That's the problem statement itself is we are going to consider axial dispersion, meaning Ca will be a function of Z. Okay, so all the C is not a function of R, but Ca will be a function of Z. Okay, which would mean that there will be dispersion along this direction. Okay, there will be dispersion effect in this direction, but not in this direction. If there was perfectly mixing in this direction, Ca would have been constant in this direction also. Okay, all right. So that is what we are going to assume. Then what else? And some of the constants we can assume the value or denote them. DAZ would be the dispersion coefficient, like diffusion coefficient. Okay? But you have to remember that there's a difference in the diffusion and dispersion. Dispersion, when you talk about dispersion, you're actually thinking of mixing due to eddy formation, flow conditions. Okay? But diffusion need not have this atomic level transport. Okay, and that would happen even in solids. There is diffusion. But whenever there's a highly turbulent flow, you think of another diffusive effect. It's not atomic migration. It's not the migration of atoms on the molecular level. It's basically mixing effect that happens due to turbulence or eddy formation. But physically, they both look the same, and they both can be modeled by a diffusion phenomena, okay, which is given by the Fick's law, etc. Okay. So, except that the diffusion coefficient for atomic diffusion and the eddy diffusion will be different. Okay. So, DAZ I'm going to call dispersion coefficient, but remember this need not correspond to atomic level phenomena only. Okay. So this will include the effect of turbulence as well, or eddy diffusion also. And of course, Ca0 is the inlet feed condition of the reactor. Okay. Now we are going to. So let's look at the model equation. So the model, we are going to assume the steady state. Okay? So we assume steady state and the rate accumulation. I'll repeat it multiple times so that it's etched in your mind. Yeah. There's a question for it. Yeah, okay, Shalu. Okay. So yeah, so I'll repeat what I meant by dispersion and diffusion. So dispersion is more like a more general term. Sometimes they use community they use it interchangeably, but you have to remember one thing, that is so remember this flux equals to minus d del C by del X. Okay. Now this is a phenomenon. This is basically a you can say this is basically constitutive equation of a phenomena where concentration gradient causes flux. Okay. Now, what is the mechanism of that flux? Okay. That may depend. It can be actually atomic level diffusion. Okay. So, for example, if you have a solid, okay, and you expose it to gas environment, okay, these gas molecules will actually penetrate inside, slowly diffusing, okay, and this will actually go inside the material. That is basically atom finds a concentration gradient here, and that's what happens. Okay, but at the same time, like when you take up a, let's say, if you take up a sugar, if you take up a bowl of water, okay, and you put some water in there and then put some granules of sugar, let's say a cube of sugar, okay, and you stir it, okay, you stir it very fast, very high Reynolds number. When it becomes turbulent, okay, then what's going to happen is there's going to be diffusion of these material, okay, in this medium, right? That is happening because of the eddy formation. So the eddies would be formed. Okay, these eddies will basically, what will they do is they will actually homogenize, try to transport the matter or whatever is the solute is there. You try to transport it in a different region of space, okay, different region of the volume, and there will be eddies of all length scales, etc. We will not go into that detail. Okay, his entire this, a couple of lectures discussion on that. So how eddy forms, how concentration is diffused, how to mathematically deal with that. But basically, this is this other mechanism by which this but solute concentration actually spreads out. Okay, so this is essentially the concentration spreading out effect, both here and here, but the mechanisms are very different. Okay, but overall it can be captured by this equation. Okay, both appear to have appear to like a diffusive phenomena or diffusion, and they both can be captured by the single equation, except that d value because since the mechanisms are different, so d will be different. So the flux that is arising over here would be given, if you know del C by del X, then the d value would appear to be different if this is due to this turbulent flow or due to eddy diffusion versus atomic diffusion. That would be different. Okay? This would be eddy diffusion. Okay, so d would be different. That's all. But overall, the governing mathematical model equation is still the same. Okay, does that make sense? Does that make sense? Okay, all right. So let's proceed then. So, well, I was going to write this anyway, plus rate generation. As I said, I will write it every time we have to use it so that it's kind of etched into your mind. And that would be given by minus del by del Z of the flux. Okay. And rate, I have just assumed a first order, so K minus KCA. Okay. And rate accumulation would be 0 because of steady state. Okay. So, and then this GA must have two parts. One is the convective, which is given by CA into UZ, and then other is diffusive, which is given by minus dA from the Fick's law, del CA by del Z, minus KCA equal to 0. Okay, so that will give me an equation that would look like minus. Now I also know that Vz is constant with Z, so del Vz by del Z will not be, so that I can take outside. But the Vz by del Z term will not be there, minus Vz del CA by del Z plus dA del square CA by del Z square minus KCA by G. This is our governing equation, right? So you can see this is second order equation. Okay, you could have expected that. Okay. Now what this so far it looks it's not very complicated. What is important here is what is non-trivial in this problem is the boundary conditions. Okay? The boundary conditions are non-trivial. What are the boundary conditions? How do you find the boundary conditions? Now, I just want to draw your attention to this effect of dispersion, axial dispersion. Okay? So again, I'll just draw. Let me draw the figure. You have something entering which is constant concentration, and so something is entering. You have a feed which is entering with some concentration C is 0. Okay, but something happens at this as soon as it enters this point. Okay, something happens. There is of course, there's a flow, but it's continuous. Okay, but there's a sudden diffusion that starts to occur as soon as it enters. Actually in this direction, there is you can think of like the solute is sucked into the reactor suddenly, instantaneous, like this instantaneous sucking in happens over at this x equal to 0. Okay, it's something like if you recall the CSTR. Okay, when you have feed that is entering with CA0, okay, and inside here, as soon as it enters the CSTR, due to homogenization, okay, the solute is immediately spread over entire region. Okay, that leads to a very important effect, which is the CA here is not equal to CA0. The concentration inside the reactor is not the same as the concentration of the feed. Okay, and so this is something similar happens here. you have a kind of this homogenization effect due to this diffusion. Okay, so that leads, what does that lead to? That leads to a kind of discontinuity in the concentration at x equal to 0. Okay, so concentration at, so Ca at x equal to 0 plus is not equal to Ca at x equal to 0 minus, which is actually Ca0. Okay, Ca at x, so right next to this point, okay, Ca is not equal to Ca0. There is an immediate infinitely fast sucking in due to diffusion. Okay, so the instant sucking in that leads to discontinuity in concentration at this point. Okay, why? By the way, we'll discuss more about this nature of infinitely fast uh, this tendency of the diffusion equation being infinitely fast is something that we'll see more in detail later. Okay, when we talk about PDEs and diffusion equation. But that is typically correct. Diffusion is infinitely fast phenomenon. It travels, the information travels at infinite, it's instantaneous. Okay, so all right. So anyway, that is detail to be discussed later. But I just want you to understand the physics of this, which is that the boundary condition is such that at this point is going to be a discontinuity in concentration, right? All right. So what is the actually boundary conditions? What are the boundary conditions? So at x equal to 0, okay, what we do is we can do the flux balance. So the steady state. So at x equal to 0, we do the flux balance. Concentration profile is continuous inside the reactor. Of course, you are right. Inside the reactor, it's continuous. But at the inlet point, at the inlet x equal to 0, there is a discontinuity. So Ca is not equal to Ca0 at x equal to 0 plus. That's what I'm saying. Okay? This quantity is not equal to Ca0. Okay? So in the region of interest, which is inside from here to here, my first point, yeah. Understand that? That's good. Okay, so at x equal to 0, what we do then? Do the flux balance. By the way, chemical engineers must have studied that. It's called Danckwerts boundary condition. Okay, very very important boundary condition called Danckwerts. I'll write it later. It's called Danckwerts boundary condition. Here. Okay. All right. So, and that is that's the reason I'm taking this example, because remember, equations are there. The physical, the equations are there. The model equations you can easily frame, but the physical nature of the problem is very much decided by the boundary condition that we use to solve it. Okay? That's where your physical insight is actually will be useful. Okay? So always pay very very important, very good attention to the boundary conditions, how they are used, why they are used, etc. Okay, so here I'm going to use flux balance condition. So flux balance at x equal to 0. Okay. So flux in will be equal to flux out because it's steady state. Okay. So what is the flux in? That will correspond to there is no diffusive flux in because concentration is constant before this point, right? So what I'm going to write down is flux in would be Vz into Ca0. That's completely convective flux. Okay, so only convective. Okay. There is no concentration gradient before this. Okay, we're assuming that feed has a homogeneous concentration along z direction. Okay, this is z direction. Okay. Okay. So this is convective, but the flux that is leaving this boundary at x equal to 0, okay, that will have both the components, which would be Vz into Ca at 0 plus, and then there will be diffusive component that will be Vz del Ca by del Z at 0 plus. 0 plus would mean right next to the boundary towards on the right hand side. Okay? that is x equal to some epsilon value. Okay, that limit epsilon tends to 0 from the right hand side of the 0. Okay, so this would be your boundary condition. So that is the reason, because of this term, there is a discontinuity that arises. If this term would not have been there, I get CA0 equal to CA0 plus. So in that case, you can very well start. So if you know the feed concentration, you can start inside the reactor, the concentration is going to start with the feed concentration. Okay, and then it will decay with some kind of profile. But because of the axial dispersion, that assumption is violated, and you have to be careful in applying the boundary condition. Okay, so you must have studied without axial dispersion. You must have solved it with CRE class, CRE course, how the profile looks like, right? So, but we are going to have this extra term over here. Okay, all right. So that is what happens at x equal to 0, and x equal to L. That's another boundary we have. What do you expect here? So at x equal to L, you can think of like Z. Just a second, I'm coming to your correct move. Yeah, I think I'm going to get a very important question. I just saw it. Just wait a minute. There's infinite. Just a second. Okay, there's a question. Finite section variation velocity change due to acceleration. No. Okay, so this is suction is basically, what I mean is diffusion, and that is of the solute, not the entire flow. It's not a pressure gradient. It's not a pressure gradient. It's suction. By suction, I would mean the diffusive suction, not the convective suction. Okay. So does that make sense, Amit? I'm not so suction. I'm not referring to pressure difference. I'm referring to the concentration gradient would lead to diffusive transport. No, so what your question? Your question is, if there is infinite suction ability, shouldn't velocity change? No. So as I said, suction does not affect velocity. In the way I'm defining suction, it's not with respect to velocity. Velocity suction would be like a pressure difference. Okay, there's a difference in pressure that would lead to velocity section, right? But here I'm looking at the concentration difference. Okay, so basically solutes going from, well, you can imagine, for example, if there is infinite, so maybe I can elaborate a bit more on that. So infinite suction would be something like this. You have a medium, and let's say you have a such kind of medium where you just add a drop of, let's say, an ink. Okay, and the moment you add, the entire this whole fluid becomes blue with the same, and it's instantaneous effect. Okay, so suppose you add a blue ink here, the moment it joins this medium, it's perfectly spread out. Okay, there's no color difference in between any two points. Okay, so there is no, in that sense. So suction is probably, yeah, I understand that's not a very good word to use, but I would say, well, spreading, infinitely fast spreading, that's probably a better word. Okay, so yeah, I think that's all the problem. Okay, Anand, again at x equal to 0, what's happening? Okay, I'll go back. So it is at x equal to 0. Well, it's just what happens at x equal to 0. You just let me know which step, which logic you did not understand, which part you did not understand. At x equal to 0, I have both convection and diffusion playing a role from right hand side, whereas only convection playing basically giving rise to flux from left hand side. Okay, because of this diffusion from right hand side, if you just equate the flux on the both sides, we are going to get this equation. Okay, that suggests basically that Ca at 0 plus will not be same as Ca0. Okay, there will be an additional value. It will decrease by a little bit more. Okay, from Ca0 because of this suction effect. Because of this, well, I should not call it suction, but the finitely fast spreading effect inside. Okay, so as soon as this guy joins the reactor, because of the axial dispersion, there's infinitely fast spreading that happens along the z direction inside, and because of that, Ca at this point dips suddenly to a certain value which we do not know yet, and we have to find out. But whatever that value is denoted by this. Does that make sense? Anant, does that make sense? Does that make sense, Anand? Hope you reply yet. I hope that should be fine. Okay. Okay. Now at z equals to L. Okay. Uh, what is going to happen now here? Now we know that Ca. So one thing, another important physical, the fact which is related to the setup is that concentration of exiting field, exiting stream will be the same as Ca at L. Is that convincing enough? That means whatever Ca we obtain from the calculation at L minus, okay, that would be the same concentration of the exiting field. So as soon as it exits, the concentration remains the same. Whatever concentration we obtain at this point inside is the same as concentration that is outside, and then it again remains constant. Okay, so this way concentration is constant. This side concentration is constant. Okay, so because of that, if you just again apply this, let's say this is L plus delta Z, and then you apply the flux balance. Okay, flux that is entering and flux that is leaving. Flux that is entering will have two parts now. That would be one would be the Ca at L into Vz, convective part, and then minus del Ca del Z, okay, at L and Vz backwards. Okay. That would be equal to, right hand side of flux would be Cal into Vz. Because exit feed concentration is still the same as the concentration inside the reactor. Okay. Because of that, these two terms cancel out, and I get del Ca del Z equal to 0. Okay. These are the two boundary conditions I'm going to get. Okay. All right. I hope this. So I think this is very important for you to understand. Okay. The use of especially this Danforth's boundary condition. Right. Okay. Any question on that? So let me rewrite this Danforth's boundary condition again. Okay, that would be Uz into Ca0, okay, x equal to 0, z equal to 0, okay, Uz Ca0 equals to Uz Ca minus Ca into del Ca1 del Z, and z equals to L del Ca del Z 0. Okay. All right. So now what do we do? One of the very important step generally modeling a problem is to non-dimensionalize, right? So we all have probably studied that. We don't want to talk. We want to minimize the number of independent constants that actually affect the behavior, or basically which are responsible for the way an unknown behaves with respect to other unknown, right? So here, the way Ca behaves with respect to Z okay, will depend. Here I have how many constants do I have? I have Vz, I have Ca naught, I have dA. Okay, these are the three constants which appear to basically affect the equation as well here. Diffusion equation here is Vz Ca over Z plus Vaz equals Ca over dx square minus Qc. Okay, so four constants. So there are four things which are appearing in our problem: Vz, Ca naught, daz, and Q. These are the constants. So constants there appear to have four constants that would decide the nature of Ca function as a Z. Okay, appear to have four constants which may decide the nature of Ca and Z. Okay, which are Vz, dA, K. Sometimes I write it daz or dA, but please don't find that. And then CNR. Okay. But it turns out that actually you only need two constants in some kind of combinations of these, right? And that is what basically what we try to do when we try to non-dimensionalize a problem. Okay, so let's non-dimensionalize, and you all remember the procedure. You have to basically you have two variables, Ca and Z. Okay, you have to basically look at the scales of these variables in the problem. Okay, and divide by that scale to find the non-dimensional variable, right? So here my scale of Ca is Ca naught. Okay, I mean typical concentration we are talking of is the feed concentration. Although we do not know what's going inside, but at least we know that we're going to start with the concentration which is there in the feed, right? Which is Ca naught. So at least there's a scale, concentration scale in the problem which is given by Ca naught. Okay, so that would be, so I'm going to call Ca by Ca naught as Ca star. So Ca star, this is the product, this is star. So then compute these two, the product, this is star. Okay, and Z. How will I non-dimensionalize Z? So there is a Z star and multiplied with the length of the reactor. There's only one length scale, which is reactor length. Okay, so I have a reactor length L, so that would be my that would be the way. Okay, so now if you substitute these expressions over here, this would give me dCA would be equal to Ca naught, dCA star, dz would be actually equal to L into dz star. Okay, so just substitute it back in the the differential equation over here. Okay, that would lead to minus Vz into dCA dz is what? dCA naught dCA star by L dz star plus dz del square Ca would be del Ca naught del square Ca star divided by L square L Z star square. You should be familiar with this procedure, I guess. Minus A Ca naught U star. That is equal to zero. Okay, so now I will multiply this entire thing with, let's say, I want to get rid of this. So let me multiply L squares by multiply this by L square over dAz is entire equation I have to multiply with this term. Okay. So yeah. So like that, I think the new L square C A naught cancels out, L cancels out, I get minus Z L variable L. Is that all right? Z C naught cancels out, L cancels out of the D. Okay. Then C star by Z star plus C naught cancels out, L square cancels out. This could be just L square C, because I've chosen this to have unity coefficient. Okay. L square C star divided by Z star square minus here C naught cancels out, L square by dz. Okay. Now I can identify two constants. This entire thing, this entire thing. Okay. So yeah, okay. VZL by dz. So VZL by dz. Where does that? Anand, you have another question. Well, that is Anand, your question is why is C8L minus is Cl plus? Well, because that is the nature of the exiting stream. That is, whatever has been formed is going to exit out. That's how you define exit stream. Okay, so whatever is formed up to that point will be what is going to be extracted out. That is the meaning of exiting stream. Why is that? L squared dz. Well, I just that's a term that I just multiplied it so that this invert of that, so that I get 1 here. That's all. Nothing more important. I just multiplied so that this becomes 1. I just rearranged thing, okay, so that I get 1 here and these numbers change. That's all. Is that all right? Yeah. And Anand, was that answer satisfactory? Because whatever you're exiting, right, that's the meaning of exiting stream. Whatever has happened up to L, before L, will be the same that is coming out. Okay, so that is the basically justification of having C8L minus as same as C7 plus. Okay. Any more doubts? Yeah, these are very important things to understand, because that depends on you. That decides the result. Okay. These assumptions will decide the result, which can be drastically different. Okay. If you don't take the correct boundary condition, your result will be absolutely absurd. Okay. All right. So now this quantity, anyone knows what is this called? Velocity into length divided by diffusivity. Velocity into length divided by diffusivity. Anyone knows? You guys have appeared for gate recently. You must know this thing. Anyone? Yeah, absolutely right. Peckler number. This, which is Peckler number. Okay, so this is a number I'm going to refer to as PE. And so this number essentially is basically it's a dimensionless number first of all. Okay, so length remember diffusivity is L square by T. Okay, so L by T is velocity, 1 L cancels out. This is a dimensionless number. This is also dimensionless number. Okay, L square by what is this number? Probably I don't remember exactly what this number is called. This is another dimensionless number. I will denote it by R. These two numbers decide the behavior. Yeah, I think damn polar number. You're right. I think so. I'm not. I will have to recheck. Okay. So Peckler number is basically it gives me relative importance of two effects. One is diffusion, one is convection. Okay, convective diffusion is how fast The diffusion is with respect to convection. Okay? So if dAz is large, okay, okay, and convection is small, okay, then this number will be small. Okay, so the flow is very fast as against the diffusion tendency. Tendency to diffuse is very small, and flow is very large. Okay, so suppose there was no reaction, let's say, and if there was no reaction, and let's say, and there was a flow, and you let entered a speck of dot or probably a ink somewhere over here. Okay, and so happened, and as this guy reaches at the other end, this does not spread much. Okay, quickly moves from this end, this the ink spot quickly moves from this end to that end without spreading much. That would be basically high Beckler number. Okay, and if it, but the flow is say very small, so that by the time you reach from here to here, you completely, this entire region becomes colored because of your ink spot, so that it completely spreads out. That would be like a small, diffusivity is very large as compared to velocity, Z into L. Okay, so in that case, this is like a small Beckler number G. Okay? So this is basically relative importance of convection to diffusion. The same manner, this R is it's basically implies relative importance of reaction and diffusion. Importance of reaction speed, reaction rate, diffusion rate. How fast diffusion occurs versus how fast reaction occurs. These two numbers, these two numbers which reflect two different kind of relative importance. So remember, we had all the three terms present: velocity, that is convection, diffusion, and reaction present in our original equation. Okay, so depending on which term dominates with respect to which one, you can combine to form two quantities which would tell two different kind of relative dominances of different phenomena, and that will essentially decide the nature of how Ca star depends on Z star. Okay? So this is my equation, which we can directly write down. So I'll just write it as just a couple of more minutes and I'll be through. So my equation becomes del square Ca star del Z star square minus Beckler number into del Ca star by del Z star minus R Ca star equal to 0. Okay. Now, how about boundary condition? So we already have the boundary conditions, right? So we can just write down at Z star equal to 0, which is actually Z equal to 0. Because remember, Z star is Z into Z by L. Okay. I had the condition which is Vz at Ca 0 plus minus dA del Ca 0 plus divided by derivative of Z equals to C0 Vz. Okay. And if I just write down in terms of non-dimensional variable, this becomes Vz Ca star into Ca0 minus dA Ca0 del Ca star by L del Z star, okay, equals to Ca0 Vz. Now I can cancel out Ca0 from all these. Okay. That would give me Vz. Okay. So I can write down Ca star minus dA dA over Vzl. Okay. Equal to, I'm going to multiply with del Ca star by del Z star. So we divide by Vz to 1. So that would imply this Ca star minus 1 over Beckler number del Ca star by del Z star. That is what happens at Z star equal to 0 and at Z equal to L. what I know is del CA by del Z equal to 0. That would imply CA star CA 0 del CA star divided by L del Z star that is equal to 0. That would give me del CA star by del Z star equal to 0. That is what happens at the beginning. Okay. So these three things. Now I have diffusion equation in terms of CA star and Z star. Okay. So knowing Peclet number is R, polar number, and implementing these boundary conditions, we can solve this equation. So what we have essentially done, we have not yet gone into how to solve. Is it for field modulus? Which one is field modulus? Let me check. Is that field modulus? Diffusivity and reaction. Okay, probably. I'll have to check that. Yeah, I don't remember exactly what is that called. But here, well, field modulus is defined for catalyst. Right. This should be called the same thing, maybe, probably. Reaction and diffusion. Well, field modulus is usually referred for catalysts. So here, I don't know. All right, so I guess I will stop here. All I did was we have a model equation and we have reduced the number of variables, number of constants that we require to solve. It turns out that from 4 we can reduce to 2 variables, which are Peclet number and R. Okay, and we can talk in terms of CS, the non-dimensional variables, where you're talking in terms of the fraction by which Ca changes with respect to net heat concentration, that is Ca star is equal to Ca by Ca0, and what part of the reactor you are in, meaning Z star 1 would be like end, Z star 0 would be the beginning, Z star half would be like halfway through, and so on. And similarly, Ca star half would be like half of the heat concentration, and so on. Okay, so in terms of those variables, we can actually solve this equation. Now next class I'll talk about how we apply shooting method. So it's just a problem where we have to apply shooting method and see some important points which would be necessary when we try to solve it using shooting method. Okay. All right. So we'll stop here. And any questions? Okay, then we'll start the class tomorrow.